Let me thank for this wonderful opportunity to give this talk in front of a distinguished audience, many of whom are specialists both in quantum transport and non-equilibrium many-body physics. So in this talk, I copied here two of these themes of our nice workshop. I'm going to try to transgress these boundaries. As you have seen from the previous talk, usually when people do this coupled charge spin transports in nanostructures, they use single particle formalism such as Kubo formula or Landau-Lifshitz-Gilbert formalism. And then there is a whole new, different world of non-equilibrium dynamics of many-body systems when people use much bigger guns in terms technically, but then they are confined to very small systems. And then often they study some kind of very fundamental problems that are not maybe directly related to any experiment, like quenches in the Hubbard model and so on. So in this talk, I'm actually going to use the physics of the Hubbard model and some of the techniques from this non-equilibrium dynamics of many-body systems, but I'm going to apply them to pretty much the same problem of spin torque that was introduced in the previous talk. So the most important information, there's a lot of information on the slide, but the most important one is this website in red. So if you see any reference in red ink on my slides, you can quickly jump to this website and get the paper in PDF rather than trying to struggle with proxies, web publisher websites, and so on. So let me first acknowledge my collaborators on this project. So these are two of my former graduate students who just finished this summer, my former postdoc, and then also very important collaboration with Professor Feiguin regarding density matrix normalization group for auto-equilibrium problems, and Professor Plehech, who is in mathematics department in Delaware and help us with all kinds of algorithms. So during this COVID lockdown, you know, you're writing papers, reading physics, then you have to relax your brain. So I was reading all kinds of books and articles, and I ran into this interesting one, which says, you know, scientific paper is obsolete. And it doesn't mean that we are going to stop papers per se. That will be remain #1 medium to disseminate scientific information, always much better than any kind of book. But what they really mean here is that, you know, maybe besides just conventional paper or talks, you should also include all the new technology. And in this talk, especially for the audience who is not familiar with spin torque physics, I'm going to put a lot of movies. So like even if you cannot capture all the equations or formal discussions or, you know, things related to Spintronics community, you should be able to follow this final outcome of our research, which is a bunch of movies scattered through my slides. And so whenever you see the movie, pay attention because they're conveying much better picture of what's going on than all the words and equations that I'm going to try to sell you. Starting with spin transfer torque, this is pretty much #1 topic in Spintronics. It is very interesting that it was originally initiated purely theoretically, and probably people did not even believe. I know exactly few people who told me this, that it should exist. Eventually, it also earned this Buckley Prize in condensed matter physics. So the basic idea of this original 1996 prediction by Slonczewski and Berger is that you have to have two ferromagnetic layers. One has fixed magnetization, the other one has free magnetization. Free means magnetization can move in any way you want. Fixed means you have to put many other layers not shown here to fix this magnetization. Then you inject electrons, and these electrons are going to get polarized in the direction of the white magnetization. Then they're going to go through a spacer, which could be a normal metal or an insulating barrier. And once they arrive to this free layer, quantum mechanics tells us that only component parallel to magnetization can go through. And then you can ask yourself, what happens to the transverse component? Well, the transverse component has to be absorbed. And once you realize that transverse component has to be absorbed, you also realize that this is a beautiful many-body non-equilibrium problem, which eventually is not just something that we study from the viewpoint of theoretical physics, but it also has numerous potential applications, and it is directly accessible to experiments. And the question then is how you're going to treat the dynamics of this magnetization. Essentially, the second layer is now absorbing spin angular momentum. That's the meaning of this transverse component disappearing. And this magnetization is going to have dynamics due to that absorbed spin angular momentum. And then you can ask yourself, should I use quantum mechanics on this or some other formalism? And the standard in spintronics community for the past 25 years has been to actually consider this fixed magnetization as a classical vector of fixed length. Like magnetization is free, but it has a fixed length, which is the requirement of the Landau-Lifshitz-Gilbert classical equation. And then the only thing that you need quantum mechanics for is you compute this non-equilibrium spin density, which is pretty much this electronic spin density in the second layer. And once you take the cross product between non-equilibrium spin density and this classical vector of magnetization, you will get what is called torque. So this is actually, there are many other ways historically people have been using to compute torque, but this is the most efficient one, which operates both in this standard magnetic tunnel junction and spin wall tri-layers, as well as in the case of this newer frontier of spin orbit torque you heard in the previous talk. And so how do you calculate this non-equilibrium spin density? Well, typically you would use some single particle quantum transport formalism, Cavendish or Kubo as in the previous talk. You take a trace of that with the Pauli matrices, and that gives you this non-equilibrium spin density, and then taking the cross product is trivial. Once this magnetization is initiated, it could perform all kinds of motions. You could start, for example, from the North Pole, and then the magnetization could perform some motion on the unit sphere and end up on the South Pole. And if you generate that kind of non-equilibrium dynamics of magnetization, that becomes a resource for memory because you have up and down as 0 and 1. And this is example of this red circle where you see that this has already like being implemented as a device you can buy. At the moment, it is not widespread, but if you believe in this technology, you could take your retirement money, invest into the stock ticker MRAM, and or there's some other company being developed in Belgium, and hope that in 10 years this would be so important that you would become rich and you can retire early or something like that. So there is actually another 7 applications you could have using spin torque. You would have this beautiful random number, pure random number generators. If the magnetization starts precessing rather than flipping, you would end up with a microwave oscillator. You could detect microwaves. You could generate spin waves or magnons, and you could also have memristors. In other words, the spin torque devices could become a resource for neuromorphic computing. And so from this viewpoint, people have been doing these calculations, doing these experiments for 25 years. It looks kind of easy and straightforward. It's pretty much a computational effort. If you're not familiar with this topic, as I said, here is now the first set of movies. So here I'm actually using the formalism we developed in this series of papers, so-called TDNEGF, time-dependent non-equilibrium Green function, same as in T-quant, coupled to Landau-Lifshitz-Gilbert equation. And I'm going to inject electrons which are going to get polarized along the x-axis, and they're going to hit a bunch of these free localized magnetic moments. If you sum them up, you get the free magnetization. They're going to interact, and you will see in the movie what happens. So here is the pulse, and you see very quickly I was able to flip local magnetic moments in this free magnetic layer from up to down. And the movie was basically giving you, like, see here, I'm injecting a current pulse. So there is a current pulse. As soon as the current pulse is active, this guy starts moving. After some time, you see they're going down, and you can see like incoming spin current, outgoing spin current. The difference between outgoing and incoming spin current, because they do not have any spin scatters or spin orbit coupling, is actually torque. That's one way to think about torque. But now you could see that from my formulas, if I try to inject electrons which are parallel to the free magnetization, nothing happens. And that's kind of trivial because, of course, cross product is zero. Nevertheless, I did have some strange discussion with one of the referees on our papers. What would happen if you try to inject down electrons onto up localized magnetic moments? And even though I know that this is also not going to lead to any effect, the referee was trying to pull some papers again from 20 years ago, Boltzmann equation, semi-classical transport, blah, blah, blah. And this formalism is far superior to anything from 20 years ago because it's a quantum classical formalism which evolves everything in time, quantum electrons, classical localized spins, and you can see that nothing happens. So when the referee was trying to talk to us verbally, we just told him, watch the movie and see that what you're saying is not possible. So in any case, the message here is that unless you have non-collinearity between the incoming flux of moving electronic spins and the spins which are going to receive the torque, nothing happens. And this has been a paradigm for the past 25 years. However, an experiment came up in 2017. There was actually, honestly, two earlier ones, but they're kind of obscure. One was sitting on archive, unpublished. There is another one that did not capture too much attention. In any case, this one did capture a lot of attention. As you see, it has a viewpoint in which Sergei Rajdin, who is a very inventive experimentalist and can also do theory, and he has actually written a couple of papers, theoretical ones, following our discussions. He said, you know, let's take the spin valve that people have been using for torque since the early days, and let's cool it down to 1 Kelvin. And you could ask yourself why nobody did that before. Well, first of all, people usually consider these spintronic devices to be useful only in the operated room temperature, and they probably didn't want to bother with this cooling down. And he cooled down the spin valve to 1 Kelvin, and basically then he has one ferromagnetic layer with up magnetization, and then he has another ferromagnetic layer with also up magnetization, and in between is a normal metal layer. And since he is at such a low temperature, typically in real devices, nobody actually really tilts the magnetization of the left magnet. What they do, they rely on thermal fluctuations, basically tilting magnetization. And then when you pass a current at some point randomly, and that's why there is a distribution of the switching times, you're going to reach non-collinearity and initiate this spin transfer torque process. But in this case, you're at 1 Kelvin, everything is frozen, and technically nothing should happen. But he observed something. That's why he published PRL. And actually, it is remarkable that in the paper, without actually having any theoretical support, much of the insight is aligned with later theory we developed. But what they tell you that there is no really well-developed theory of treating everything quantum mechanically, both electrons and localized magnetic moments receiving the torque. And also, he says, you know, the proposed effect is not the torque, which actually turns out not to be correct. And then they actually came out with some hand-waving explanation saying that maybe the reason why we observe something non-trivial, which means magnetization is moving despite the fact that everything is parallel, collinear, is that there are some magic quantum fluctuations, that there is some kind of quantum fluctuations at very low temperature that are also going to tilt magnetization away from collinear directions and initiate a torque. And surprisingly, or strangely enough, people jumped on this and tried to develop these different theories, picking up on these quantum spin fluctuations, but quantum spin fluctuations do not exist in ferromagnets because they're already in the ground state. For antiferromagnets, it's a different ballgame. And here's a quote from Bill Mullin, whose papers I really like to use in my teaching courses on quantum statistical mechanics, who tells you can only put words after you develop the formulas, rather than you put words and, you know, try to put some physical interpretation and then build the formulas around them. And in a nutshell, what our theory says is that if you have parallel electrons hitting collinear localized magnetic moments, indeed, you're not going to see anything. If you hit with the non-collinear electrons, you're going to see the standard Slonczewski-Berger torque, as I showed you a slide ago in a movie. But there is a new effect which has been completely missed in the literature, which is that if you inject collinear electrons onto the localized quantum magnetic moments or quantum spins, and these electronic spin is collinear but antiparallel to the localized spins, then you will see something new. And we believe that this is exactly what Urarzin observed in this PRL. And so since I'm mentioning this, you know, that we need to treat everything quantum mechanically, let me kind of give you my overview of different formalisms that us and other people have been developing while paraphrasing this string theory guys who says they have 3 roads to quantum gravity. So in the field of this, electrons interacting with localized spins, which is a quintessential problem from anything spintronics, magnonics, and applications, what you need to develop is a theoretical or computational approach to electrons interacting with localized spins. So in some talks, we have used this formalism, which is like single particle quantum transport, where time-dependent non-equilibrium Green functions are helping us to see how electrons interact with classical localized magnetic moments. And this is what I was using in those movies I showed you. You could try to map those, if you want fully quantum treatment, you could try to map quantum spins, which is sine qua non to use Green functions because Wick theorem doesn't like spin operators. You could try to map them to bosonic operators, and this is what we have been doing since 2014. But it turns out to be extremely complicated because you're going from finite Hilbert space of localized spins to infinite Hilbert space of bosons. And there is like decades of efforts to understand what is the proper way to map without introducing unphysical effects. In this recent pedagogical paper, we discuss all kinds of drawbacks of textbook Holstein-Primakov transformation, Dyson-Mallet transformations, and so on. So in any case, it's very difficult to execute this Cavendish diagrammatics while mapping spins to bosons, which is why in this talk, we actually keep the original representations of spins using matrix operators in a finite dimensional Hilbert space, and then electrons interact with these original spin operators. And in order to handle this problem, we switch to time-dependent density matrix renormalization. For example, in all of the calculations I'm going to show you, we typically have about 70-something sites. We use, let's say, about 10 electrons, and we use about 10 spins. And the size of the total Hilbert space in a brute force approach would be 10 to the 14. And that's, of course, undoable, which is why you need this density matrix renormalization of matrix product states, and then you need to evolve that smartly using adaptive tDMRG algorithms and so on, which is going to employ it in the rest of the talk. Before I actually start with these heavy guns, let me use a very light gun. This is the kind of calculation that you can implement in some of your courses, for example, on computational physics, even though nobody has ever studied this in American Journal of Physics or computational physics textbooks. So you take a Gaussian wave packet and you polarize that packet. So the polarized packet means you could polarize the wave packet either along the x-axis in this case, or you could polarize it along the z-axis, and then you hit the Heisenberg model. And you also allow some hopping between the sites. It's not just a plain Heisenberg model. It's more like what is called Kondo Heisenberg model. And if you inject up electron onto up spins, of course, nothing happens because this is an eigenstate, and eigenstate do not evolve in quantum mechanics. But if you inject down spins onto this collection of localized up spins, then you're going to see dynamics. And dynamics is very strange because what happens in this situation is that localized spins are changing, but they are not moving away from the z-axis. And this is why Landau-Lifshitz-Gilbert equation could never describe anything like this. That's why this is purely non-classical magnetization dynamics, because in Landau-Lifshitz dynamics, the only thing that can happen, you start from z-axis magnetization, and then it rotates away from z-axis. Here it doesn't rotate, it is shrinking. And this is a purely non-classical effect, which actually has to do with entanglement. So like entanglement is also something that Landau-Lifshitz equation could never capture. And so what we see is that injected collinear but antiparallel electronic flowing spins are causing shrinking of these local magnetic moments. And there is also change of purity of both of these quantum systems. And you can actually see what kind of states are excited here once you look at the probabilities. So it looks like kind of magnon, but again, this is not a magnon. This is not a periodic system from textbook physics. You see actually electronic spin and all these other spins being excited. Then you ask yourself, but okay, this is something strange. It's a purely non-classical. Is it a torque or something completely different, as they hinted in PRL that the effect they see is not a torque? Well, you could say, what would happen if I inject something which is tilted with respect to local spins? And something tilted in quantum mechanics means just a superposition of up and down spins. There is no anything rotating. And if you inject this component doesn't do anything. This one does something. And once I put these figures next to each other, I realize it's the same thing. The only thing which changes is that these probabilities are divided by 1/2 due to this prefactor here. And so this is the simplest picture of torque, and people have picked up on this, and you can quickly write a paper and understand something. But if you want to inject 2, 3, 5, 10 electrons, you need bigger guns. That's why we are shifting to this Hubbard model physics. We set up again either up or down spin hitting this localized spins. And here is again the important part of the talk. Watch the movie. So like here are the localized spins. Electrons are coming in. Once they enter this region of free magnetization, you see that localized spins are jumping from -1 to 1. So like toward 1. Now with many electrons, we can actually flip the spin, but the X and Y and X component of the spins are completely frozen. So this is again purely non-classical dynamics, in which the only thing you see is it is as if the spin just flips from up to down without ever rotating. And of course, this can never be described by any type of classical Landau-Lifshitz-Gilbert equation. Since we now have full machinery of quantum antibody physics, where we have quantum electron systems and quantum localized systems, we can also ask the question, what is being transferred? So here, for example, you nicely see how the total spin of all the electrons is getting reduced, while the total spins of all localized spins are changing, the Z component. And so that means electrons are really transferring their angular momentum to the localized spins. In standard picture of single particle quantum transport, you never see this. What you see is basically electrons are coming in, their spin is forever precessing in the magnetization of the second layer, because electron spin is not eigenstate of this magnetization of the free layer. And then you ask yourself, well, where is the torque? Because it looks like I deposit something, I remove something. It turns out when you average over many different K parallel vectors, you will see that because of many different K vectors, everything averages down to just one lobe of these oscillations, and everything is confined to the interface. You can also get contribution from evanescent states, which never contribute to transport. But you never understand, like, okay, I see something is being averaged and something decays to 0, but how do I see that electron is transferring actually angular momentum to local spins? And you never see this because you don't have both systems being discussed as a quantum mechanical system exchange spin angular momentum, as you have in this fully quantum antibody picture. So now this system also generates long-range entanglement. Here I could actually invoke autopilot and stop my talk. This is a beautiful talk which somehow disappeared from online on highly entangled quantum matter. And the reason why I'm showing it is that somewhere around 6th minute, when he starts introducing entanglement for kids, he tells you that ferromagnet is a mundane system which is not entangled because all spins are up. This is what is called separable state in quantum mechanics. And then he says, well, maybe with some effort of a heroic proportion, we could start generating entangled state of ferromagnet. And he says this is enormously difficult to do because if you do just 2 states superimposed, this will be very fragile. And eventually he says, if you want to generate something magnetic, which is highly entangled in equilibrium, you must shift to quantum spin liquids, use the quantum information theory to discuss them, which is so-called topological entropy and so on. It turns out that once you shift out of equilibrium, what we predict in our paper is that with no effort, you would actually see that highly entangled states are being generated from a mundane ferromagnet simply by hitting them with this flow of incoming spins, which are collinear. The highest entanglement is when they're actually outside of this realm of Slonczewski-Berger torque. And here I wrote analytical state. The DMRG would tell you that the coefficients in this state are not all the same, but for the sake of deriving analytical formula, I make them all the same, and I also get a maximal entangled state. And then what we see is that when the geometry is this antiparallel collinear, they get the highest von Neumann entropy of half of the system, which is one standard way to quantify entanglement of non-equilibrium many-body system. Furthermore, if I compute what is called mutual information, which is the von Neumann entropy of the first spin of the chain, von Neumann entropy of the last spin of the chain, minus von Neumann entropy of two of them together, viewed as the subsystem, then I see that this mutual information remains non-zero all the way to infinity. And there is actually an analytical result of this you can see in the paper. And so this means that at arbitrary distance, first and last spin remain entangled due to quantum spin torque, which is example of highly entangled quantum matter with a long-range entanglement. And so just to give you another example, the previous talk has discussed a lot about antiferromagnets, and this is indeed a great frontier, the latest frontier in the spintronics community. And here I'm actually showing futuristic device. I know that many people like to fabricate this. We predicted it from this first principles single particle quantum transport theory. If you take this new two-dimensional bilayer antiferromagnet chromium iodide and you couple it to this TaSe2, then you're going to get non-equilibrium spin density once you pass a current only on this first layer, and that would allow you to generate non-equilibrium phase transition from antiferromagnet to ferromagnet. So you see what happens here is like first pulse, they're antiferromagnetic, pulse comes in, magnetization is being switched. The only way the magnetization can switch in this classical description as a classical vector is by rotation. They're now stable ferromagnet, even without any current flowing. The second pulse comes in, and I reversibly, or nature reversibly, switches back this chromium iodide to antiferromagnetic phase. But this is all classical. The question is what would happen if you start treating this antiferromagnet quantum mechanically. And so here is again example of torque on classically treated antiferromagnets. And for the people who come from strongly correlated community in this audience, they might be puzzled, you know, what does it mean, classical antiferromagnet? Well, in spintronics community, people like to think that antiferromagnet is just a collection of sticks of a fixed length, which are oriented up, down, up, down, up, down. And if you hit them by torque, for example, here I'm going to hit insulator by torque, electrons cannot propagate, but I can see that there is a spin wave going through this region, and then eventually I can transfer that magnon on the other side and switch magnetization of ferromagnetic layer. So like, it looks like that if you want to do antiferromagnetic spintronics, the only thing you need is somehow Landau-Lifshitz-Gilbert equation applied to this collection of up and down sticks. But it turns out that if you go to real materials, and this is kind of very puzzling, people in spintronics community like to use nickel oxide. They consider nickel oxide exactly in this fashion, but then it turns out that the same nickel oxide in strongly correlated community would require a Hubbard model. And so if you set up this kind of system and you have a layer of Hubbard electrons and you have a normal metal underneath, which is sending the spin-polarized electrons, you can actually see something very interesting, which is that these electrons, even though they do not flow directly through this Mott insulator and they cannot enter because of the Hubbard gap, these electrons can basically transfer angular momentum to Mott insulator half filling, which is antiferromagnetic. And one other issue is that without any anisotropies impurities, this is also a system which has localized spin being zero, which is the meaning of the green color on every side. So like in the Mott insulator at half filling, the antiferromagnet is a kind of at the same time spin liquid because there is no any kind of vector. So there is no any kind of ability, even in equilibrium, to talk about classical up and down sticks. If you put a single impurity, as we do here pedagogically, you could actually invoke the Neal order of up and down sticks, but these up and down sticks are always less than one, and so they are not really anything that would allow you to use the Landau-Lifshitz-Gilbert equation. And this is a well-known thing that classical Neal state is not eigenstate of the Hamiltonian. Instead, because of the real quantum spin fluctuation of zero-point motion antiferromagnets, for example, in this case of 4 spins, you end up having the superposition, which is entangled state, which gives rise to the 0 expectation values. And again, the movie is the most important. If I run the movie, you will see that what happens is that even though electrons never enter into the region of this antiferromagnetic multi-insulator, they do exchange angular momentum with the localized magnetic moments generating from localized electrons in the multi-insulator, and there is a new ordering, which is now a kind of zigzag ferromagnet that is transmutation of this antiferromagnetic multi-insulator with 0 magnetization on each side into some new type of order in which you have non-zero magnetization on each side, and also it's non-uniform zigzag ordering. And this is my last slide just to summarize. So for 25 years, nobody really believed that you would need any kind of quantum theory of spin transfer torque when you treat both electrons, which are flowing spins, and localized spins quantum mechanically, until this experiment showed up. They're at very low temperature, but you might have some of these effects persisting all the way to room temperature. And eventually, all of this stuff would play a great role in any kind of quantum computing, with individual quantum bits based on spins would be manipulated by injecting current and jerking them with quantum spin torque. Everything I discussed is encapsulated in this basic figure that if you have collinear geometry, nothing should happen according to Slonczewski-Berger. Only collinear geometry does give you non-trivial phenomena, but the new thing is that if you have this collinear but antiparallel geometry, you can actually get a torque that does not exist in any kind of Slonczewski-Berger picture. And finally, all the calculations I showed you is either quasi-1D or 1D ladders and chains. Eventually, to model realistic spintronic devices, we would like to go into 2D and 3D. We would like to attach fermionic reservoirs, which should go toward this talk that Xavier Weintel gave, and have a continuous energy spectrum, which is sine qua non in non-equilibrium many-body physics oriented toward realistic systems to include dissipation and circuits. But this is a kind of task ahead which will take many years to solve and develop.